Convolution Neural Network, CNN. CNN stands for Convolutional Neural Network, a type of deep learning algorithm specifically designed for image recognition tasks. CNNs are inspired by the visual cortex of the human brain and are highly effective at detecting patterns and features in images. The fundamental building blocks of a CNN are convolutional layers, pooling layers, and fully connected layers. Here's a brief explanation of each. Convolutional layer. This layer applies filters, also called kernels, to the input image to detect specific features like edges, textures, or shapes. The filter slides over the entire image, and at each position, it performs an element-wise multiplication with the local region of the image and then sums up the results to create a feature map. The resulting feature map highlights the presence of the detected feature in the input image. Pooling layer. The pooling layer reduces the spatial dimensions of the feature maps obtained from the convolutional layer. It does this by downsampling and keeping only the most important information. The most common pooling operation is max pooling, which selects the maximum value from a local region of the feature map. Fully connected layer. After several convolutional and pooling layers, the fully connected layers process the extracted features and make predictions. These layers are typically used at the end of the CNN and have neurons connected to all the neurons in the previous layer, which helps in learning complex patterns and relationships. Example image. Let's consider a simple example image to demonstrate how a CNN works. Suppose we have a grayscale image of a handwritten digit, 3, with a size of 28 by 28 pixels. Each pixel in the image has a value between 0 and 255, representing the intensity of the grayscale color, 0 for black, 255 for white. The CNN architecture. Input layer. The 28 by 28 image is the input to our CNN. Convolutional layer. The convolutional layer will use multiple filters, let's say 3 by 3 filters, to detect different features in the image, such as edges and corners. Each filter will slide over the entire image, producing several feature maps. Activation function. After the convolution operation, each element of the feature maps goes through an activation function, commonly ReLU Rectified Linear Unit, to introduce non-linearity to the model. Pooling layer. The max pooling layer will reduce the size of the feature maps by, for example, taking the maximum value in 2 by 2 non-overlapping regions. Fully connected layer. Finally, the fully connected layers will take the flattened output from the pooling layer and make predictions. For a digit recognition task, the last fully connected layer may have 10 neurons, since there are 10 possible digits, 0 to 9, and each neuron's output represents the probability of the input image belonging to that digit class. Output layer. The output layer will use a softmax activation function to convert the logits, raw predictions, into probabilities. Training. The CNN is trained using a labeled dataset of handwritten digits, typically a large number of images of digits with their corresponding labels. The model learns the best filter values and weights through a process called backpropagation, which minimizes the difference between the predicted probabilities and the actual labels. Inference. After training, the CNN can be used to predict the digit in new unseen images. The input image, e.g., the digit, 3, will go through the CNN, and the model will output probabilities for each class. In this example, the CNN will ideally output a high probability for class 3, and lower probabilities for the other digits. Note: the above explanation is a simplified version of a CNN and does not cover all the intricacies and variations that exist in real-world CNN architectures. Actual CNNs used for image recognition tasks are typically much deeper and more complex, like VGG, ResNet, or Inception.